Okay, welcome everybody. Our first speaker today is Didem Gozupek from Turkey. Didem is an associate professor in the computer engineering department of Gebze Technical University in Turkey. Didem works with structural and algorithmic graph theory and optimization problems in communication networks. And Didem is also our friend. She visited Poland several times, and she is also a very nice person. And we are very happy that Didem accepted our invitation. And we invite you to listen to her talk entitled Stable Matchings and Equimatchable Graphs. And if somebody has questions, it will be possible to put this question on Facebook.
Okay. Thank you very much, Magda, for offering this talk. It's so nice to see you in person soon. So let me start my talk and sharing my screen. So the title of my talk is Stable Matchings and Equimatchable Graphs. So I will first talk about stable matchings and the well-known Gale-Shapley proposal algorithm, which eventually led to a Nobel Prize in economics, but it's actually in graph algorithms, I think. And I will also talk about maximum matchings. And then I will move on to the minimum maximal matching problem, which is also related to stable matchings. And finally, I will talk about equimatchable graphs, the literature on equimatchable graphs, as well as several works that I did in collaboration with other colleagues on equimatchable graphs. And finally, I will pose some open questions. So starting with the basics, what is a graph? Graphs are mathematical structures used to model pairwise relationships between combinatorial objects. So a graph is made up of vertices. In some literature it's called nodes or points, which are connected by edges, also called links, or in some other literature, lines. So for instance, this is a graph consisting of vertices 1, 2, 3, named 1, 2, 3, 4, 5, 6, as well as some pairs of edges between these vertices. So this is called a simple graph. So more formally, it's a combinatorial object consisting of an ordered pair of vertices, G, VG, EG, and where VG is a set of vertices and the edge set EG is denoted by EG, where it's a set of edges which are unordered pairs of vertices. So in other words, an edge is associated with two distinct vertices in a simple graph. In the same graph here, we already had the vertex set, and in the edge set is consists of the vertices between 1, 2, 1, 5, 2, 5, 2, 3, 4, 5, 3, 4, and 4, 6. Its graphs have a very wide range of applications. For instance, routes in road networks, they can be modeled using a graph with edges corresponding to road segments between intersections. This is one of the most concrete examples for a graph. In social networks also, this is also a concrete example. We can model acquaintance relations. If two people know each other, we have an edge between the vertices corresponding to those people, and if they don't, we don't have an edge. So we can analyze social networks by representing them using graph models. And sometimes they are not always that concrete. They can be modeled, but for instance, job assignments can also be modeled. So let's say that we have a set of people and a set of jobs. If certain people are capable of doing a certain set of jobs, then we have an edge between that person and that particular job. And we may have edge weights given to the edges or given to the vertices even. So there is a wide range of problems, and the job assignments can be modeled by this. If we may want to assign one job to a particular person, at most one person at a time, etc. So we also have many applications of graphs in scheduling and graph coloring, which is again a very wide literature. For instance, we can schedule committee meetings into designated weekly time periods, and we may have certain restrictions in that scheduling. For instance, if two people, if two committees have a common member, since a person cannot be at the same time in two different committees, one committee, so we cannot assign two committees to the same time. So the question here is, what is the minimum number of time periods we need? We can model this problem also as a graph where each committee is represented by a vertex, and if they have at least one common member, those two committees, we have an edge between them. So the minimum number of time periods here corresponds to the minimum number of colors that may be given to the vertices of this graph, so very widely known as the coloring problem. So the restriction here is that if there's an edge between two vertices, they cannot receive the same color, meaning that they cannot be assigned to the same time period. I will talk about matching theory in general in this talk. So let me first give the definitions of a matching. First of all, matching is a subset of the edges. So it's actually an edge set with some certain properties. A matching in a graph is a set of non-loop edges with no shared endpoints. For instance, in the first graph here, this is not a matching. The bold edges represent the edges of the matching in each graph. So the bold edges in the first graph do not constitute a matching because these two edges share vertex 1 as a common endpoint. So this is not a matching. But in the second graph, the edges between 1 and 3 and the edge between 2 and 4, they constitute a matching because they don't have any endpoints. The third one is also a matching. It's just one edge, but it's is consistent with the definition. Okay, so even one edge may be considered a matching. Of course, the interesting problem is to find, to maximize these number of edges so that it is still a matching. So we call the maximum matching problem that I will talk about. So perfect matchings, the vertices incident to the edges of a matching M are said to be saturated by M. For instance, here in the first graph, the edges between 1 and 3, here the vertices 1 and 3 are saturated by that particular matching. And a perfect matching is a graph, in a graph is a matching that saturates every vertex. For instance, in the first one here, every vertex has an incident one edge. So it's all vertices are saturated by this matching. That's why it's called a perfect matching. Not every graph has a perfect matching, and not every matching is a perfect matching. For instance, here in this graph, these two, the matches between 1 and 3 and 2 and 4, they do not constitute a perfect matching because the vertex 5 is unsaturated. Let me also give the definition of bipartite graphs. A bipartite graph is a graph whose vertices can be divided into two disjoint and independent sets that we call U and V, such that every edge connects a vertex in U to a vertex in V. So the edges can be only between these two pairs of sets, these two sets. This is a bipartite graph. One set U is shown in blue and the other is shown in red, and the edges are only between red and blue. So there are also some alternative definitions of a bipartite graph. It's a graph without any odd length cycles. It can be proved that if it has an odd length cycle, then I cannot partition its vertex set into two disjoint and independent sets with this property. And another definition is a graph that is two colorable. So its vertices can be colored using two colors, one with one part hue, one color, and the other with the other color. So a complete bipartite graph, a bipartite graph is called a complete bipartite graph if every possible edge is part of the bipartite graph. So here, for instance, in this graph, we have every possible edge between these two sets U and V. So that's why it's called a complete bipartite graph. So let me talk about the stable marriage or stable matching problem, whose efficient solution led to many life-saving applications that we will see, and hence a Nobel Prize in 2012. So the problem is we are given n men and n women. In other words, we are given a complete bipartite graph with equal size parts and each with size and. In addition, we are also given an ordering of preferences for each element. So each element on one side has a preference ordering of the elements in the other side. So if a vertex is in part U, it has a preference list containing all the vertices in part V, and vice versa. So we want to establish unstable marriages. Here, the term marriage actually corresponds to a matching. So we're actually looking for a matching in a bipartite graph. So what does stability mean here? That's the whole point. Stability means the following. If man X, so some vertex in one part, and women A, some vertex in another part, are paired with other partners. So if they are matched to other vertices, not to each other, but X prefers A to his current partner, and A prefers X to her current partner, then they might leave their current partners and switch to each other. So this marriage is not stable. So in this situation, we say that the unmatched pair, XA, is an unstable pair. In a stable matching, we don't want any instability. So if then the matching is stable if we don't have any unstable pairs. For instance, we are given men X, Y, Z, W and women A, B, C, D. So, and the preference lists are as follows. For X, X prefers A the most, and then B, and then comes C, and then D. While, for instance, I'm not going to read all of them, but W prefers C the most, and D the least. And after C comes B, and then A. And for instance, here, actually, the whole graph is a complete bipartite graph, and we are looking for a stable matching. Here, the matching, which is represented by bold edges, meaning the edges between X and Y, A, Y and B, Z and D, and W and C, is a stable matching because one can check that we do not have any unstable pairs in this matching. X and B, for instance, if we look, X prefers A, so X and B cannot be unstable because X is already matched to the partner that he or she is most happy with. And same thing applies for all other pairs. So this is one example of a stable matching in this complete bipartite graph. So in 1962, this problem was solved in polynomial time. And the application here is the college admissions problem. I will talk about the applications of the stable marriage problem after presenting the algorithm. So let's see what the algorithm is. It's called Gale and Shapley's proposal algorithm. They proved that a stable matching always exists and can be found using a relatively simple algorithm. So we are given preference rankings by each of n men and women, and the idea is to produce a stable matching using proposals and by maintaining information about who has proposed to whom and who has rejected whom. And each man proposes to the highest woman on his preference list who has previously not rejected him. So we have an iterative algorithm here. And if he receives exactly one proposal, then we stop and we use the resulting matching. Everybody is happy. Otherwise, every woman receiving more than one proposal rejects all of them, except the one that is highest on her preference list. And every woman receiving a proposal says maybe to the most attractive proposal received. And then the iteration continues like this until everybody is matched. And this algorithm eventually produces a stable matching, which always exists, which is also proven by Gale and Shapley. So in 1962, they proved that this algorithm produces a stable matching. In 2012, the Nobel Prize in Economic Sciences was awarded jointly to Alvin Roth and Lloyd Shapley for the theory of stable allocations and the practice of market design. Alvin Roth was instrumental in putting this algorithm into practice, into modifying it, and by modifying it to solve some really important real-world problems. For instance, one application of stable matchings is assigning new doctors, new graduating medical students to hospitals. In the 1960s, Alvin Roth was interested in approaching economics like an engineering discipline, using theoretical ideas to improve real-world systems. And he wanted to diagnose matching markets that were not working and adapt the Gale-Shapley algorithm to help them work more efficiently. Roth, with some support from the National Science Foundation in USA, began looking at the National Residency Match Program, so-called NRMP program. And it's a system that assigns new doctors, graduating medical students, to new hospitals around the country. And in the 1990s, this NRMP program was struggling because new doctors and hospitals were often both unsatisfied with its assignments. So Roth used Gale and Shapley's work to reshape this matching algorithm so that it produced matches that were more stable. So that was one really important application of the stable matchings. And the second one is assigning users to servers in a large distributed internet service, which are called content delivery networks. There also we have some preference lists, and we want a stable matching between users and servers. Another example is the pairing of students to public schools, and this took place in New York City. And New York City, like many cities, they enabled students to select a high school by ranking their preferred choices from among all of its schools. So before Roth and his colleagues redesigned it, the public high school assignment process was really a mess, a trouble. So about 30,000 students in a year were left unmatched, and they ended up at schools they had not even listed. So this happened like this. So the New York City public high schools were asking applicants to list 5 most preferred schools. So they each had a preference list consisted of 5 schools. And the acceptance, rejection, and waitlist procedure was applied. And those students who were not placed after the 3rd round, they were assigned via administrative process to a school for which they have not expressed any preference. So this is where the system failed, actually. This system suffered from congestion because of the too many applicants, and resulted in about 30,000 students per year to end up with the administrative process, and hence ending up schools that they had not even listed. So as soon as a version of these applicants proposing Gale-Shapley algorithm adjusted for, of course, they couldn't use the algorithm immediately because every application has its own requirements. So they had to adjust it for regulations and customs of the New York City. And in 2003, only about 3,000 students ended up with the administrative process. So compared with 30,000, this is actually a 90% of reduction compared to the previous years. The real life-saving application is, I saved it for the last one, is helping transplant patients find a match, and maybe it's the most motivating part for the Nobel Prize. So in kidney exchanges, for instance, there are also these preference lists representing the compatibilities of the patients with the kidneys. And in 2009, and only in the United States, according to the United Network for Organ Sharings, there are 95,000 people in the waiting list for kidneys. So only 13,400 of them could be transplanted a kidney, and 9,300 of these are from deceased donors, and the rest are from living donors. And the waiting list becomes longer steadily every year, unfortunately, and this is only for kidneys, not for other organ transplants. So the main problem for living donors is the medical incompatibility for things like because of blood type or other genetic things, there might be some incompatibilities. So Alvin Roth said that this was a history of victory after victory in a battle that we are losing. So by adapting this Gale-Shapley algorithm, they were able to save many lives, actually. So that was the most important application, probably, of the Gale and Shapley algorithm. So after all these applications, let's move on to a little bit of more theory. So a maximal matching. Maximal matching in a graph is a matching that cannot be enlarged by adding an edge. So we cannot obtain a larger matching by adding another edge to a maximal matching. If we try to, then it's no longer a maximal matching. For instance, in this first graph, these two edges constitute a maximal matching. Well, they are already a perfect matching as we have defined. But the second one is not a maximal matching because I can still add the edge between vertices 2 and 4 and obtain a larger matching that contains the first one as a proper subset. So it's not a maximal matching. A maximum matching, different from maximal matchings, is a matching of maximum size among all matchings in the graph. So with maximum, we are actually referring to the size. Every maximum matching is a maximal matching, but the converse need not hold. Of course, every maximum matching is maximal because otherwise, if it were not maximal, we would be able to add another edge and obtain a larger matching, and that would contradict with its being maximum. So for instance, in the first graph here, this is a maximum matching. It is of size 2, and it's a maximum one. The second one is not a maximum matching because it has a smaller size. It has size 1, but it's maximal because it still cannot be enlarged by adding another edge. So maximum matchings can be found in polynomial time using Edmonds-Blossom algorithm. Maximum part can be found in polynomial time. So what about the other version? That's what I will talk about today. The minimum maximal matching problem asks for a maximal matching with minimum size, not the maximum one. For instance, in this particular example, we are actually seeking this matching between 2 and 3, which is of size 1. So shorthand notation, let's call this MMM problem. It's extensively studied in the literature due to its wide range of applications. For instance, in a telephone switching network. Consider a telephone switching network built to route phone calls from incoming lines to outgoing trunks. The worst case behavior of such a network, which is actually the minimum number of calls routed when the system is saturated, this can be evaluated by a minimum maximal matching. A second application related to the first part of my talk appears in the so-called stable matchings, the stable marriage problem. for instance, involving a set of institutions and applicants. Gale and Shapley's proposal algorithm that we previously talked about enables us to determine a stable matching between, for instance, as we said, medical school graduate students and hospitals. And it is easy to see that it can be seen that a stable matching is necessarily a maximal matching, because otherwise there would be at least one more pair of institution and applicants where both prefer to be matched to each other compared to the current situation. However, the well-known Gale-Shapley algorithm, which finds a stable matching in a bipartite graph, may leave some institutions and applicants unmatched. And this is clearly not a desired situation. And we can see that the number of unmatched institutions and applicants is bounded above by the number of the remaining vertices. So after the removal of a minimum maximal matching, since a stable matching is necessarily a maximal matching, we have this situation. So another application of minimum maximal matchings is in problems where the number of applicants can be very large, so that finding a stable matching does not always yield some desirable results. So it might be a situation where the number of applicants can be very large. For instance, this is indeed the case during the university admission examination in my country, Turkey, where each year over 2 million students apply. And here, the National Examination Office places students to universities by giving priority to the preferences of students with best scores. So this is always criticized whether we should have a central nationwide examination or we should have a system more similar to in US, and we have some cultural differences in that, in ethical differences. So this is a big discussion, but let's say that, and because of this scale, departing from the central system totally does not seem feasible. So one option might be departing from the idea that the examination score cannot be the only criterion in the student placement procedure. So we may have a situation like the following. After the first placement results, it may be convenient to establish some short lists of the same length based on the initial preferences of students and universities, and which are, of course, now represented by exam scores. And these short lists can be obtained by constructing a stable many-to-many matching, where each student and each university has the same number of choices. And this might be represented by a regular bipartite graph. That is a bipartite graph where each vertex has the same degree, has the same number of neighbors. And once we have the short lists, students and universities can have a second round to express their new preferences, which are this time based on interviews and a better knowledge of each other. So criteria other than exam scores for institutions or university reputations for students can now be taken into account. So universities can apply their own criteria in this part of the selection procedure. So a stable matching obtained from this regular bipartite graph with new preferences will be the ultimate placement result. So this is another motivation for studying the tractability of minimum maximal matching problem. So I will talk about some results on the minimum maximal matching problem in certain graph classes. So let me first talk about graph classes and why I would be interested in graph classes. So whenever a real-life problem is modeled with graphs, it is crucial to understand the structure of the graphs obtained in this way and whether this structure is of any help in solving the related problem. So a graph class is a set of graphs defined by having a particular property. Like we said, bipartite graphs, for instance, are a graph class, trees, or you can define your own graph classes with having certain properties. According to this website, graphclasses.org, and I just recently checked it, there are more than 1,600 graph classes in the literature. So the problem of deciding whether a given graph belongs to a graph class is called the recognition problem of this class. And sometimes the actual application is important only in that particular graph class. So the general version of the problem may not be important, and it might be sufficient if I solve the problem in a certain graph class, depending on the application. So an NP-hard problem can sometimes be solved efficiently in some special graph classes. In such cases, polynomial time exact algorithms can be tried. Or on the contrary, sometimes an NP-hard problem remains NP-hard even when the input graph is restricted to a special graph class. So this gives us more information into the combinatorial structure of the problem and the difficulty of the problem. So a systematic analysis of such polynomial and NP-hard cases gives us important insights about the real difficulty of the problem under consideration. So the real life problem can be modeled by a graph model, and so the recognition of the graph class is important here so that we can use results from the literature to solve that real life problem in that graph class, which is important for the application. So for instance, coming back to the MMM problem, the minimum maximal matching problem, here I have summarized the known results in the literature. So this tree is a hierarchical tree, so meaning that, for instance, bipartite graphs are a child of perfect graphs because all bipartite graphs is a certain class of perfect graphs. And bipartite graphs with maximum degree 3 is also a proper subset of bipartite graphs. So there is this hierarchical structure. Grids, for instance, are both planar and bipartite. Okay, so it has two parents here, so it's not really a tree here. And here, the red parts are the graph classes for which the MMM problem is proved in the literature to be NP-hard. And the green ones are the graph classes for which MMM problem is known to be solvable in polynomial time. And so there are these unknown graph classes, chordal bipartite graphs, grids, and interval graphs. The complexity of MMM problem is not known for these graph classes. For interval graphs, for instance, I and my colleague worked on it pretty hard, and our belief was that it's polynomial, but and we worked really hard on finding a dynamic programming algorithm, but we couldn't do it. So this I have posed this as an open question at the end of my talk. Hopefully one of you might be able to solve it, and I would be interested in reading or listening to it. So now I will be talking about another graph class called Equimatchable graphs, and the definition is related to maximal matchings and, of course, the minimum maximal matching MMM problem. So a graph is called equimatchable if all of its maximal matchings are of the same size. So MMM problem is in general NP-hard, and it may even be NP-hard in certain graph classes, as I told here. If I have a graph where all maximal matchings are of the same size, and believe me, the definition is sounds restricted, but actually this graph class is pretty large. We have many in this graph class. So it's maximal. If all maximal matchings are of the same size, then I can start with any edge and try to extend this edge to a maximal matching one by one in a greedy way, so that it can no longer be enlarged. So I can obtain any maximal matching. Since all maximal matchings are of the same size, this will also be the minimum maximal matching. So it's a graph class where equimatchable graphs are a graph class where the minimum maximal matching problem are easily solvable in polynomial time. And of course, the maximum matching problem, because MMM, the size of the minimum maximal matching, is equal to the size of the maximum matching in equimatchable graphs. For instance, in this graph, I have shown all maximal matchings, okay? And we can actually see that they are of size 2. But in this graph here below, we have 2 maximal matchings, one with size 2 in between 1 and 3 and 4 and 6. And I have another maximal matching, which is of size 3. So this graph is not an equimatchable graph. So an interesting question is, of course, can I recognize in polynomial time whether a given graph is equimatchable? If someone gives me a graph, can I check in polynomial time whether it's equimatchable or not? So the answer for this was proved in the literature as yes. So recognized in polynomial time. The literature for equimatchable graphs was already rich when I and my colleagues started working on it. And here are some known examples that 3 connected planar equimatchable graphs were characterized, and as well as 3 connected cubic equimatchable graphs. Cubic meaning every one of them has degree 3. Equimatchable graphs with GRAPHS at least 5 were characterized. GRAPHS is the length of the minimum cycle in the graph. Factor critical equimatchable graphs. Its definition is a little bit more complicated, but not very important at this point. So if you're interested, I can. Factor critical graph is a graph where whenever I remove some vertex from the graph, the remaining has a perfect matching. And this is true for every vertex. Factor critical equimatchable graphs with connectivity 1 and 2. 1 was actually completely characterized. 2, the characterization was not complete in the literature, but there are some really nice results. And edge-stable equimatchable graphs was, I was not in this work, but my colleague worked on edge-stable equimatchable graphs. So the first work that I done with in the equimatchable graphs literature was this one. Equimatchable graphs are C2k plus 1 free for k at least 4. So this is the main result and of the paper, which is also the title of the paper. To see this, let me give some definitions. So an induced subgraph is a subgraph obtained by dilating a set of vertices. So which vertices? That's the question. So a subgraph induced by, so more precisely, a subgraph induced by a set of vertices T is the subgraph obtained by dilating all vertices except T. So we have the vertices in T and all the vertices among T, but not any other edge. And C2k plus 1 free for k at least 4 means that C corresponds to the cycle. So free means I don't have it as an induced subgraph. So this means that our equimatchable graphs do not contain induced cycles of or induced odd cycles of length at least 9. So odd cycles of length at least 9 are forbidden in equimatchable graphs as induced subgraphs. And this is actually the first family of forbidden induced subgraphs of equimatchable graphs. So another work that I did was on equimatchable claw-free graphs. So a claw is this graph. So it's actually a bipartite graph with size 1 on one side and size 3 on the other side. It's actually a complete bipartite graph, sizes 1 and 3. So if I forbid claw as an induced subgraph in an equimatchable graph, we have a complete structural characterization for this, and it's a little bit more complicated. But the good thing is that this led to a recognition algorithm of equimatchable claw-free graphs with complexity big O m to the power 1.407, where m is the number of edges. So what's the meaning of this? Equimatchable graphs can already be recognized in polynomial time, claw-free graphs as well. If I combine these two properties, we already have a polynomial time recognition, but our characterization here leads to a more efficient recognition algorithm than it is already known by other results in the literature. So another is I think some work that I enjoyed working on very much, but it's still under review. It's a triangle-free equimatchable graphs. And so we forbid cycles of length 3. So I don't have a triangle. Equimatchable graphs. This is a really wide graph class. We provided that a complete structural characterization of triangle-free equimatchable graphs. And even more importantly, given a non-bipartite graph, our characterization implies a linear time recognition algorithm, which is really fast. But for bipartite graphs, there are some results in the literature which characterized bipartite equimatchable graphs, but their complexities are not very efficient, still polynomial. So our motivation was here at this point was to focus more on bipartite equimatchable graphs, because if we improve the already known algorithm for bipartite equimatchable graphs, actually the algorithm is not explicitly specified, but the characterization in the literature leads to an algorithm. Then it would imply better running times for the recognition of triangle-free equimatchable graphs as well. So that's why we started working on equimatchable bipartite graphs, and we could not obtain a more efficient algorithm, but we had some nice characterizations which provide more insight into the structure of such graphs. So let me give some definitions. For an equimatchable graph, an edge is said to be a critical edge if the graph obtained by the removal of this edge is not equimatchable. So this edge is of critical importance. If I remove it, my graph is no longer equimatchable. An equimatchable graph is called edge critical. Shorthand notation is we say it's ECE graph, edge critical equimatchable, if every edge is critical. So if every edge is critical, then we call it an ECE graph. Our study in this work, it reduces the characterization of equimatchable bipartite graphs to the characterization of bipartite ECE graphs. This does not give us an algorithm, but a nice information and characterization into the structure of these graphs. So we also provide some characterizations of bipartite ECE graphs in this work. So I have some open questions. I hope you will be interested in. One interesting open question is, in the last work I mentioned, we obtained good results, but not the ones that we hoped for. So I think it could be improved even more. So an interesting open question is to obtain an efficient algorithm that recognizes whether a given bipartite graph is equimatchable by generating these ECE bipartite graphs, and finding a more efficient algorithm for bipartite equimatchable graphs. And my final open question is the question that we worked on and could not solve yet, but currently we are not working on it. So I think maybe one of you can solve the complexity of the minimum maximum matching problem in interval graphs. So this is the end of my talk.
Okay, thanks a lot, Didem, for your very nice talk. I think everything was very clear and well done. I would like to remind that it's possible to make some questions to Didem via Facebook. I don't know whether somebody made the question. Maybe Julian will check this. Okay, it is still possible.
Okay, I'm not stopping sharing because the questions might be related to some part in the presentation.
Okay, for me it was very nice to listen, to hear talking about matchings in a little bit different way than in the context of Hall theorem, because I think the Polish students knows only this way of talking about matchings. And yes, my question is whether have you possibility to talk about this topic, about these matchings with the students, for example, during lessons, to work together later?
Me or I?
Yes, you, or in general. Is some place on, I don't know, graph theory lessons for talking about this kind of things, like matchings?
In graduate classes, yes, a little bit. I mean, the stable matchings we did, and not the applications, not this much in detail, but we do mention the applications to motivate them mostly. And minimum maximal matching problem, I just mentioned it briefly in the context, and also equimatchable graphs, I showed some things in the graduate classes, not like in detail, but I had some opportunity a little in graduate classes. If that was your question, if I didn't misunderstand it.
Yeah, yes, thanks. Okay, Julian, is there something from Facebook?
First of all, Hannah raised her hand. Hannah?
Yes.
Yes, if I can, I have a questions to Didem. First of all, I would like to say a big thank you for your talk. There is very interesting topic for me. And I have a question about your open problems.
Okay.
Namely, you put the last one about complexity status for interval graphs.
Yes.
Can you say something about your approaches? I understand that they failed.
Yes.
But what kind of approaches did you try?
We strongly believed that it was polynomial because of the structure of the interval graphs, and we focused on dynamic programming algorithms to solve this problem in interval graphs. But it has been quite some time since we didn't work, but we tried many dynamic programming approaches, which failed, all of them failed at some point. So I came to some point where maybe this is not polynomial, because if it were polynomial, we would be able to find something until this time.
Yeah.
I had that idea, but my colleagues still believe that no, it has to be polynomial. So, I mean, at some point we stopped working on it. And I mean, I'm not even thinking on it in my free time now. But I think it would be an interesting point, not only because it's an open question, but because of this here. I mean, it's not known.
Yeah.
So it's known to be NPR on perfect graphs and unit interval graphs. And also for grids, it's not known.
It's not known?
For grids, we and also some other people also had a conjecture of, because the structure of grids looks very regular, but this is really misleading in the context of this problem.
Okay.
We even had this for some certain parts, if I don't remember correctly, we had a conjecture and also for them, and we even checked it with software for until some certain problem sizes. The conjecture was that it's m is the number of edges and n is the number of vertices. M times n over 3 ceiling of this. That's the size of the MMM. And for some parts, it's not. It's for certain grids, this is true, but the conjecture was also open. And so
because it's also interesting. You mentioned dynamic programming. It was my first idea about intervals and as well as grids, because it seems it should work.
I don't know, maybe we focused a lot on some, maybe we had too much effort on something so obvious. Maybe we needed a different approach for this, and maybe it's still not difficult. I don't know, but
Okay.
I would really be happy to see whether the actual results for its own MMM in TurboGraphs.
Okay, I will try to think about it, and
Okay.
I will contact with you later
Okay.
by email. Okay. So thank you once again. Very nice.
You're welcome.
We have a few comments on Facebook.
Okay.
As Super Alex says, not a question, but I really enjoyed the talk, and now I love matchings. Gibran Reynoso says, I don't have any question. It was a nice talk. Rita says it was very nice. Lalo GNS, incredible. Thanks. There is a question here. It has sense to ask the relation between EQM and cover vertex.
Equimatchable graphs and vertex cover problem. Cover vertex. Yes, that's not equimatchable graphs, but minimum maximal matching problem. There is one actually, not the vertex cover, but if we what was that? If we remove the endpoints of the minimum maximal matching, any minimum maximal matching, the remaining vertices is not the vertex cover, is an independent set. And that is true for all maximal matchings, actually. For vertex cover and equimatchable graphs, I'm not aware of any. About the vertex cover number, you mean, and the size of the equimatchable graphs. I don't recall any result in the literature, and I don't see any direct relation now. But maybe with the minimum maximal matching problem and the vertex cover problem, there might be. And I don't recall it exactly now. But with equimatchable graphs, I'm pretty confident that there is not any direct relationship or not any obvious relationship, at least.
Okay, thank you. There is another comment
You're welcome.
from Rihanna Ru. Great talk. Thanks, Didem. I love your diagram with the different classes and their complexities. And I do have
Hi, Rihanna. I know her.
I do have a question.
Yes.
Have you thought about some sort of equimatchable graphs? Well, as far as I know, a graph can have many stable matchings.
Yes, multiple stable matchings. Yes,
Multiple, but
true.
is it possible to think about some sort of joint definition with equimatchable graphs and stable equimatchable stable or something like that?
I mean, stable equimatchable, like stable matchings in equimatchable graphs, or actually the input to the problems are different. With stable matchings, we have the preference lists, and so solving, maybe stable matchings are defined on bipartite graphs, but maybe with some other stability measure involving preference lists and not in the sense that of the stable matching problem, but with some other stability measure that we might define, that could be the case. But I will come back to this point. There is this H-stable equimatchable graphs here that I mentioned in the last part of this slide. This stability in that work is different. It's a different notion, very different notion from the stable matchings. Here in that work, I know I'm not an author of this work, but it's a work of one of my good friends, so I know the paper. And here, this stability is defined as follows. Let's say that we are given an equimatchable graph, and equimatchability is not a hereditary property. So if I remove an edge, the remaining graph might be equimatchable or might not be equimatchable in an edge or a vertex. And this is not always the case for other graph classes. But here, the H-stable equimatchability, for instance, here is like, what are the equimatchable graphs such that even if I remove some edge, I don't know which one, it is guaranteed to be still equimatchable. And this stability is a different notion, for instance, here. And they also had the vertex stability version also in this paper, I think. Maybe with preference lists, with some that might be defined on general graphs, not only on bipartite graphs. Maybe that would be my answer. I hope I was clear.
Yes, thank you. There are no more questions on Facebook.
Okay, so thanks, Didem, again
Okay.
for a very nice
Stopping
opening
sharing.
talk.
Okay.
And I don't know, maybe
Thank
somebody from the organizers wants to say something. Rita or Julian, some technical things?
Juli?
Well, don't forget to follow us on the YouTube channel and on Facebook. We will be uploading this talk on the YouTube channel, and we will in about 10 minutes there will be appearing the invited the video talks from today and the poster. So don't forget to subscribe on YouTube and to follow us on Facebook, and to see our opening video of the event. And I don't know if I'm missing something.
Sí, Juli. Bueno, voy a repetir en español por si hay estudiantes que no les haya quedado claro. Entonces les recordamos que aproximadamente entre 10 y 15 minutos van a poder ver en el canal de YouTube y en Face los videos del resto de las pláticas de hoy, las pláticas por participación, así como el póster que corresponde al día de hoy. Muchísimas gracias, Didem, por la plática. Muy bonita. Thank you very much, Didem. Y pues los esperamos mañana nuevamente a las 10 de la mañana en vivo, aquí mismo por el Face. Por algunos problemas técnicos que hemos tenido, pues vamos a continuar con esto en el Face. Para la plática de nuestra invitada de mañana, que, perdón, es Rihanna, si no me equivoco. Rihanna, ¿verdad? So tomorrow we wait for you at 10 a.m. again to see in live the talk of our invited speaker, Rihanna from South Africa. I don't know.
It will be 5 o'clock of European time, yes?
Yes, depends in which part of the world you are. In Turkey, it's 7 p.m. And I think in Brazil it's different too, I am not sure. But our official time is in Mexico, 10 a.m. In Europe, Poland, 5 p.m. I don't know if somebody likes to say something more. No? So?
Yeah, I would like to thank you all for inviting me. And so I hope it was nice for everyone.
Thank you of you.
It was a really nice talk. Virtual applause.
Okay.
Well,
okay, so
see you.
See you tomorrow. Thank you very much to everybody. Muchas gracias a todos por estar aquí. Nos vemos mañana. In Polish, we need to say in Polish.
Dziękujemy wszystkim za uczestnictwo w konferencji dzisiejszej. I widzimy się jutro o tej samej porze. O 17:00 będzie mówiła Rihanna.
And maybe didn't like to say in Turk. In your language?
Like see you tomorrow?
Yes.
Yarın görüşürüz. Saat 7'de, 5'te.
Okay.
Bye.
Thank you very much. Bye.
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 Bye bye.
Bye bye.
Bye.